So welcome everybody. You know Ali, everybody knows him, and he will talk about low energy scattering and non-emission Hamiltonians. Go ahead, Ali.
Thank you. So I was telling that this is a joint work with my collaborator from Iran. I will start with the introduction to scattering theory, talk about how this dynamical formulation of scattering theory can be used to do low energy scattering for energy independent potentials, discuss its application, wormhole scattering, and then I will talk about low frequency scattering defined by Helmholtz equation. These are related to applications in optics where the potential becomes energy dependent. And then if I have time, I will also describe how this can be generalized to do scattering in the half-life. So by scattering, I mean the quantum scattering defined by a potential, and I take the potential to decay fast enough at infinity so it belongs to this class of potentials L11, which is also known as Fadaev class potentials, but I need this notation for future use, L1 sigmas. The larger sigma is, the faster the potential decays at infinity. So with this class of potentials, you know that asymptotically, the solutions of the Schrodinger equation tend to plane waves, and then you can have these coefficients at plus or minus infinity, which gives the asymptotic solutions, and you can use them to define what is known as a transfer matrix. These A's are the coefficients of right-going waves, B's are the coefficients of the left-going waves at infinity. If you take the so-called scattering solutions, you have either a left-going incident wave or a right-going incident wave or left-going scattering wave, and then the coefficients are known as reflection and transmission amplitudes. This is a special case of the general solution, and if you use this special case with the definition of the transfer matrix, you see that the reflection and transmission amplitudes are related to the entries of the transfer matrix according to these formulas. A while back in 2014, I showed that you can relate the transfer matrix of such potentials to evolution operator of a two-level quantum system. This is the evolution operator. I use U, and this is asymptotic evolution operator. This is, you can identify with the S matrix in the interaction picture. This Hamiltonian has a very nice structure. The potential appears as its coefficient, and the rest of it is a matrix which has fixed form. And here X plays the dynamical variable rather than time. So it's an effective time. And because it is time dependent in quotes, the solution of the time dependent Schrodinger equation cannot be done exactly. So you can at best write a Dyson series for the solution. So the transfer matrix is given by the time ordered product of this Hamiltonian. This Hamiltonian, it's easy to see that it is not Hermitian. If the potential is real, you can show that it's a pseudo-Hermitian. It's sigma 3 pseudo-Hermitian, which means it satisfies this condition. And if the potential is complex valued, which I also consider, then it is what is called sigma 3 pseudo-normal, which means that the Hamiltonian commutes with its pseudo-adjoint, and the pseudo-adjoint is defined by the sigma 3. Let us, since we are interested in low energy behavior, let us make the K dependence of all these quantities explicit. And let us confine our attention to finite range potentials when the potential is 0 outside a finite interval x minus x plus. In that case, you see that because potential vanishes, the Hamiltonian will vanish outside that interval. And that says this transfer matrix is the evolution operator going from x minus to x plus, rather than minus infinity to plus infinity. Now, a study of low energy or small k behavior of reflection and transmission amplitudes. That old problem. It was studied in 1980s by mathematicians, and this is a basic reference on the subject published in Journal of Operator Theory. It's a 30-something pages long, very difficult to read paper. So this was actually, we were interested in some application. We couldn't get anything out of that paper, so we sat down and tried to do it ourselves. So the idea was that, well, if I write back the time-dependent Schrodinger equation for this Hamiltonian with k-dependence explicit, I have these formulas, and the k-dependence of the Hamiltonian is very simple. There's 1 over k in front of the Hamiltonian, and then there is this exponential. So it's analytic of part times 1 over k. So we thought, just try to see whether we can get the k expansion of this evolution operator using these equations. So here is what we did. We first introduced these simple matrices and showed that they satisfy this identity. This is the identity matrix. And then you multiply U with the identity, write it in this way. You have this expansion and this formula for the evolution operator, where this G and D are certain matrices which are obtained by multiplying U by delta and gamma, these two matrices. And if you now write U in using this formula and plug it in the Schrodinger equation, you get two coupled equations for these D and G. The coefficients that appear in this equations, the important thing is that they are even functions. They are sines and cosines, but you'll see they are even functions, and that's why we could kind of deal with this. So by inspection, one can easily see that this, if we want to expand U, it will start with 1 over k, and then there is a kind of Lorentz expansion. So if we take this ansatz and plug it in the definition of D and G, we get expansions for D and G. The coefficients we call dm and gm. And there is also an initial condition for the evolution operator, right? U, that initial time is just 1, and that sets some initial conditions on these equations, which says that these coefficients vanish except the 0th one, which is just this delta and gamma. So this leads to these expansions. So we plug this in the equations, and we managed to solve the system of infinite system of equations iteratively. The solution is given in this paper. Now, once we have dmdg from the coefficients, we get these matrices. From these matrices, we can get U using this formula. And this is the first 3 terms of that expansion. It looks a little complicated, but the details are not very important. The first term is the term which goes like 1 over k. The red terms, and braces, they are constant, order 0, and then this is the linear term. These phi's happen to be the solutions of zero energy Schrodinger equation. This was also known to mathematicians, that the behavior, the low energy behavior is given by solutions of the zero energy Schrodinger equation with these initial conditions. This phi 1 and phi 2 solve this, and they satisfy this initial condition. This L I have introduced here is an arbitrary length scale, just to make all the quantities dimensionless, and you can change it arbitrarily. It's a non-zero scale. This pink G1 is determined in terms of phi 1 and phi 2. It's a little complicated formulas, but the point is that all the terms of this expansion are determined in terms of phi 1 and phi 2. And once we have the expansion for U, M is just the particular value of U at x plus at the end point. So we have an expansion for the transfer matrix. We can generalize this scheme for exponentially decaying potentials, which satisfy this. So this was for finite range. And the exponentially decaying potentials do not cause any problem. The only thing you need to do is to set this x plus minus, send it to plus minus infinity. And then you had this initial conditions for phi1 and phi2. They become asymptotic boundary conditions at x equals to minus infinity. You don't get anything, I mean, strange. It's straightforward generalization, and everything works perfectly. So this is the expansion for exponentially decaying potentials. It's the same expansion, I just wrote it in a more compact notation, introducing this A's and B's. They are just asymptotic values of phi1 and phi1 prime at x plus infinity. So we solve this at x minus infinity, and then we have the solution. From there, you can get other asymptotics. And they enter in this formula. Again, this G1 is determined in terms of this curly G and this zeta, and both of them are given in terms of phi1 and phi2. Now, once we have the expansion for the transfer matrix, we can get the expansion for the reflection and transmission amplitudes. And here something strange happens. It turns out that the formulas depend on the value of this B1. B1 was the asymptotic value for phi1 prime at x going to plus infinity. If that is not 0, you get these formulas. And if that is 0, you get a second set of formulas. And these are very different. And as you see, if you make your parameters of the potential so that you go through this B1 equal to 0, the reflection amplitudes and the transmission amplitudes jump from -1 to something which can be anything, depending on the value of B2. This is known as a zero energy resonance, which can be easily seen from these formulas. This also generalizes to the class L1 sigma. Exponentially decaying potentials belong to all L1 sigmas. But if the potential belongs to one of these, those formulas don't hold. But what is true is that you don't get a series expansion. You get a polynomial piece, and then you get a non-analytic piece, which decays faster. So you get this kind of expansion. And the nice thing is that the coefficients of the polynomial piece, the analytic piece, is the same as before. So we can use our method to calculate this the leading order polynomial dependence on K. Now, so as I mentioned, all this is related to the solutions of zero energy Schrodinger equation. Now, if you take any of these potentials, even L11, which is the largest class, you can show that the solutions of the zero energy Schrodinger equation tend to, at x plus minus, they are so that these quantities tend to constants. The derivative goes to the constant, and the function minus x times the derivative goes to a constant, which means that asymptotically, they are first order linear in x, which makes sense because if the potential is 0, you get phi double prime equal to 0. The solution is just a line. So essentially, this says it behaves like what it should be. Now, what we did was to introduce a new transfer matrix that now relates these coefficients A's and B's, which appear here at plus or minus infinity. This is the same methodology as one uses to define the ordinary transfer matrix. And this turns out also to be related to the evolution operator of some other non-Hermitian Hamiltonian, which I gave here. So we can write this transfer matrix also as a time-ordered exponential and find a Dyson series expansion for it and do perturbation theory using it and so on. For potentials which are real, this is actually Ada pseudo-Hermitian with this x-dependent, in this case time-dependent metric. And if, it's pseudo-normal with this metric. And if it's real, it is I times H0 is pseudo-Hermitian. Now, in terms of once one calculates this evolution operator, one can get this phi1 and phi2 directly out of the entries of this evolution operator. They are given by these formulas. And it turns out that the zero energy resonance is one of the zeros of M0 to 1. So remember, for the ordinary transfer matrix, the zeros of the off-diagonal elements of the transfer matrix correspond to reflectionlessness. The zeros of the diagonal elements give you spectral singularities or their time reversals. In optics, that's lasing and anti-lasing. Here, the off-diagonal element M22, its zeros will give the zero energy resonance, which is a kind of strange. So now let me talk about one of the applications. This was actually our starting point. Consider a static spherically symmetric wormhole space-time given by this metric. The omega is just the solid angle in spherical coordinates, and P and Q are some functions of the radial spherical coordinate. And we introduce a global coordinate x and make R a function of x in such a way that this q squared dr squared, which appears in the metric, becomes dx squared. And the dependence of R on this x is so that asymptotically R goes plus minus x. This x goes from minus infinity to plus infinity. And the best example is the old Ellis wormhole, where this coefficient PR is just 1, and I will only consider this case throughout. And this function R of x has this form, and this is a schematic picture of what happens. This x is the global coordinate. From minus infinity to 0, it's in one of the sides of the wormhole, and from 0 to plus infinity, you go to the other side. So you can consider these as two universes which are related by this wormhole. And R0 is a kind of how big the truth is. This is one example of this class. And we are interested in scattering or propagation of scalar waves through this space-time. This is minimally coupled scalar field of mass m. And it turns out that for this class P1 equal to 1, these are sometimes called superstatic wormholes. You have time harmonic solutions of this Klein-Gordon equation, which have this form. These YLMs are the spherical harmonics. R of x is what appears in the metric. And this psi turns out to satisfy the Schrodinger equation in one dimension. Remember, x goes from minus infinity to plus infinity. So this is just one-dimensional scattering problem for this kind of potential. I will not fix R of x, so this is general. The only thing I did was to set P of R equal to 1. And this K wave number is the square root of omega squared. Omega is the angular frequency of the wave minus mass square of the scalar field. Now, if you consider wormholes which are stable, then you have to confine yourself to low energy waves, because if the wave is high energy, then it will interact with the metric. So we consider the space-time as a background space-time. So we confine our attention to low energy waves, so it doesn't disturb the space-time. And once you go to low energy waves, you see that the first term in the potential behaves like a very high barrier if L is not 0. So the transmission is dominated by spherical waves. The ones which have angular momentum, they can't travel through this barrier. So we neglect the first term, and the potential becomes this, R double prime over R. Now, we considered a very general ansatz for the asymptotic behavior of R. R starts with plus minus x, essentially means that asymptotically it's Minkowski. So that piece is fixed by our condition. Then you can have a constant terms at plus minus infinity. And then we had very general decaying behavior for large x. Epsilon is a positive numbers, so it goes like 1 over x to any positive integer and then higher order terms. So this fits with all the examples that we have seen in literature. Now, with this ansatz, this potential belongs to this class L12. So our method will give the first two terms in the expansion of the transfer matrix. And that's why we took this to be of that form. But you see, in order for us to get something calculated, we needed this phi1 and phi2. These are solutions of the zero energy Schrodinger equation. Now, how are we going to solve the zero energy Schrodinger equation? Amazingly, you see, just look at the formula for the potential. Potential is R double prime over R. So R itself solves the zero energy Schrodinger equation. So this is a second order linear equation. You have one solution. You can get the general solution. Very easy. So we managed to do that. And this is the end result of this calculation. Reflection and transmission amplitudes have this very simple structure up to the linear terms. This C minus C plus are the constants which appear in the asymptotic expression for R. This S is given by integral of dx over R squared. Its dimension is 1 over length. So it gives you a length scale. So I rewrote the formula for the transmission amplitude. And the C plus minus, these constants, I can identify with these limits. The absorption coefficient is given by this formula. Again, we give this the derivation in this paper. So what do I mean by absorption? Suppose we are in one side of the wormhole and we send some wave. Parts of the wave is transmitted to the other side of the wormhole. So we see it as being absorbed. So just because it absorbs, it doesn't mean, we can't say it's a wormhole. It can be a black hole. It can be some other star which absorbs, or some other celestial body which absorbs this. So important thing is, so what is the nature of this absorption coefficient? Now, with our results, we could calculate this for the wormholes with this P equal to 1, and it turns out to be an area defined by this length scale 1 over S. So if you look at it, it looks like a star with some, or an object, a spherical object with some radius rho. And then terms, this OK means they are going to zero faster than linear, first order. Now, many years ago, Unruh had calculated the same quantity for a black hole in 1976. And for the black hole, it's again, if the field is massless, you have this area of the event horizon plus a linear term. We don't have linear term. Ours, the next order is faster than linear. So but by examining this absorption coefficient, one can detect whether this is a black hole or not. And for massive scalar field, there is a completely different scenario. The black hole absorption goes like 1 over k squared, so blows up. But ours is just a constant. So this gives you a signature that probably you can use to distinguish between wormholes and black holes. Okay, so next I move to from wormholes to tabletop experiments in optics. Suppose you have a slab and you shine transverse electric waves through the slab. It has an arbitrary permittivity, which can be real or complex, so you can have loss and gain. And this models the slab. The thickness is L, and I have placed it parallel to the YZ axis. Its distance from the YZ axis is A. And I suppose that this space dependence is given by this function W, which is bounded. I don't want it's not a conductor, it's a bounded dielectric medium. Now, if you consider TE waves propagating with the slab, you can find solutions of the wave equation of this form where this psi satisfies the Helmholtz equation, right? Outside of the slab, permittivity is 1, inside is given by this function W. And this is very well known that you can write this in the form of a Schrodinger equation for a K-dependent or energy-dependent potential given by K squared 1 minus epsilon. Outside of the slab, the potential is 0, so it's finite range. And inside, essentially, can have any X dependence that you can think of. Now, by low frequency, I mean that I'm looking at waves such that KL is much less than 1. Okay, so it's long wavelength. So L will give me the scale with respect to which I define low frequency or large wavelength. Now, again, the scattering setup is as before. Outside, the potential vanishes. So outside, I have plane waves to the left, the right of the slab. And then I can use this coefficients to define the transfer matrix as before. And then from the transfer matrix, I can get reflection and transmission amplitudes. Now, it turns out that this transfer matrix I could write in terms of the evolution operator for this Hamiltonian. This is a little different from the other Hamiltonian I gave you at the beginning. Actually, in 2014, actually 2013, I had first came up with this Hamiltonian. And then from this, I got the other one. So if you look at this as the Hamiltonian, the Schrodinger picture, then epsilon is 1, you have no slab. Therefore, the free particle case, free motion case, is not h equal to 0, but it's exactly sigma 3. So you see in this expression, you have e to the ika sigma 3 to the left and to the right. That's precisely how we define the S matrix in the interaction picture. Okay. Anyway, the transfer matrix is given by the evolution operator for this Hamiltonian, which you can easily write in terms of this matrix K. It's 1, 1, minus 1, minus 1, and its square is 0. So it's a nilpotent matrix. Epsilon comes here as a coefficient. Now, again, to get the evolution operator, I need to solve the Schrodinger equation, which is time dependent. Again, X plays the role of time, and that I can just identify the solution with a Dyson series of this form. And if I can calculate these terms in the Dyson series, I'll get an expansion for the transfer matrix. So the idea is here to get this Dyson series to construct a low frequency expansion for this transfer matrix. The reason is very, very simple. Look at the Hamiltonian. K comes at a coefficient. There is K dependence in permittivity because I also assume that there is dispersion. But there is a K sitting outside, and this is this K which will multiply that L, which I use to define low frequency limit. However, I mean, you need to be able to multiply these Hamiltonians, and it becomes complicated. But somehow I could see this. So the idea is, how do you multiply these Hamiltonians which have this form? So if you take, so this is an example of this HJs, the constant time K plus another constant time K transpose. And sigma plus minus I define to be the identity plus minus sigma 1. These are just Pauli matrices. Then I could show that if you multiply even number of such matrices, you get a linear combination of sigma minus sigma plus. If you multiply odd number of them, you get a linear combination of K and K plus, K transpose. And using this lemma, we could actually calculate the terms in the Dyson series. And from there, we could construct the series expansion for the entries of the transfer matrix in powers of KL, which means these coefficients T plus minus n's, we have formulas for them. This is not by iteration. We have explicit formulas, which is amazing because in the previous case, when I have energy independent potential, there is no formula and you have to do iteration, order by order you calculate. Here you get formulas. For example, the first the coefficients are given by these. This U0 is the integral of epsilon minus 1. These are moments of this epsilon minus 1, the deviation of the permittivity from the vacuum value. And then, well, you just calculate the expansions, put in the formulas for reflection transmission, expand them again, and you get the low energy or low frequency expansion for reflection and transmission amplitudes. This is the result up to terms, cubic terms for reflection and transmission. Only U0, U1 is sufficient to get this far. Again, U0 is this and U1 is that there's an X more, one extra factor of X inside the integral. Now, if you look at the transmission, if you can make this U0 equal to 0, the first three terms drops. So effectively, the slab is transparent for low energy waves. But look at U0. U0 is here. So if U0 is 0, its imaginary part should be 0. But imaginary part of U0 is just integral of the imaginary part of permittivity. That means average of the imaginary part of the permittivity is 0. That is precisely balanced gain and loss in a very general sense. So this is a kind of, there are many specific conclusions you can draw out of these formulas for specific applications that we discuss in the paper, but I need to go to the new subject to be able to finish my talk. Next, I want to show you that using this analysis for the scattering on the full line, you can also get low frequency scattering on the half line. So suppose now I have this formula for the Schrodinger equation for a potential which is defined on the half line, positive half line. Now to have a well-defined, well-posed scattering problem, I should also produce a boundary condition at x equal to 0, and I take the boundary condition to be very general, which alpha and beta are arbitrary functions, not both of them are 0. So you have Dirichlet, Neumann, Robin boundary condition all included. So this is very, very general. Now, again, because I assume that the potential dies off at infinity, then at x going to plus infinity, I have plane wave. And the ratio of the right going to left going wave is what I call reflection amplitude. In half line, you have just one reflection amplitude, which comes from, the wave comes from the right and bounces back. So this you can identify with the following situation. You have some material in the negative half line. You don't know what it is. The only information you know is its response at x equal to 0. So this red box means I have something. Maybe it's a perfect conductor, so I have Dirichlet boundary condition or other material so that I have some response through this boundary condition at x equal to 0. And again, I have my slab at a distance a from this y-axis or yz plane, rather. Now, in 2019, I had shown the following. Suppose you have the following potential little v, which is the same as capital V on the right-hand side, but 0 on the left-hand side. So this is the potential defined over the full line, right? For that, I can define a transfer matrix. I call it M. Then you can show that the reflection amplitude for this potential capital V, that is for the scattering problem on the half-line, is related to the entries of the transfer matrix for this potential little v through this formula. So you see, if you can solve the scattering problem on the full line, you have solved the scattering problem on the half-line. It's a mapping a problem from half-line to full line and then going back. This gamma is just ratios of alpha plus I beta, alpha minus I beta. It's alpha and beta should be given to me because I should know the boundary condition at x equal to 0. Now for Richter boundary condition, beta is 0. You see in the boundary condition, if beta is 0, alpha cannot be 0. So psi should vanish at the boundary. And for beta equal to 0, gamma is just 1. So this is the simple case. You put alpha equal to 0, you get the Neumann. And both are non-zero, you get Robin boundary conditions. So since I can map the problem in the half-line to the full line and I have full control of low frequency expansion for the transfer matrix in the full line, I can use this formula to get the low frequency expansion for the reflection amplitude in the half-line. So this is the formula. Again, looks complicated, but again is given by this U0, U1, which this time I define it this way. I have moved the system to the right by A. Oops. Now, I can also define the absorption coefficient as 1 minus absolute value square of R. That's the standard definition of absorption coefficient. And get the lower frequency expansion for the absorption coefficient. For Richter boundary conditions, the reflection coefficient is given by this formula. And if you have balanced gain and loss, then U0 has imaginary part 0. So this is the U0. Imaginary part will come from epsilon because 1 is real. So that essentially says the integral of the imaginary part of epsilon is equal to 0, which means balanced gain and loss. The formula for the absorption coefficient simplifies a lot. And what you can see is that there is this sign 2ak. A was the separation between the boundary and the slab. So you see, by changing the position of the slab, you can have positive or negative absorption, which means it can be used both as an absorber or an amplifier. Obviously for low frequency waves, which is kind of strange. I had not seen something like this. Okay, so let me conclude. I have shown that this dynamical formulation, writing transfer matrix in terms of evolution operator of some Hamiltonian can be used to calculate the terms in the low energy expansions of the scattering data, and the Hamiltonians which give you this formulation is definitely non-Hermitian always. For real potentials, it is pseudo-Hermitian, and for non-complex ones, it is general pseudo-normal. This formulation, last time I gave a talk on its generalization to higher dimensions. There is a generalization to electromagnetic scattering. When you do low energy scattering calculations, you need the solutions of the zero energy Schrodinger equation. And for that, we introduced a transfer matrix which has similar properties as the transfer matrix that we know. I showed you how you can use this for calculating the absorption coefficient of a wormhole. And then I showed that things become actually much better when you do deal with Helmholtz equation. Although the potential becomes energy dependent, you can actually calculate all the terms and there are formulas. You don't need to do iterative calculations. And finally, I showed that always you can reduce the scattering in the half-line to the full line. And with this machinery, you can calculate the low frequency properties of slabs put in half-line. One example I gave as an application that when you have balanced loss and gain, you can use the slab both as an absorber and amplifier just by moving it, shifting it around. Okay, these are the main references, and that's all I wanted to say today. Thank you.
Thank you very much.
Ali.
Comments, questions? Joshua is clapping, doesn't have a question.
Yeah, I have a question.
Yeah,
Am I
go ahead, Mohammed.
Professor Ali, in defining a Vx, you have defined, in case of this scalar wave transmission through stable wormhole,
Yeah.
you use Vx defined in terms of like R double dash X divided by Rx. What is the limiting value of Vx for X goes to plus minus infinity? Is it independent of X?
What is what?
Limiting value of Vx when X goes to plus minus infinite.
So with this condition, V belongs to this L12, so it goes to zero quite fast.
Okay,
It's a
all right.
scattering potential.
Yeah, because I was interested in using these results to calculate the tunneling time through the wormhole.
Yeah.
Wormhole. And one of my studies indicating that if you have a potential which is smooth one-dimensional, for a smooth one-dimensional potential whose endpoint values for large thickness is independent of the thickness itself, then the tunneling time will saturate with the thickness. So that was the reason I asked this question, whether Vx is still dependent on X when X going to plus minus infinite.
Yes, I mean, it's a nice decaying potential.
Okay, thank you. Other things may be a little absurd question because your transfer matrix M are the operators actually in this case. So what are the composition properties for this? It still holds for it?
What is?
Composition properties for this transfer matrix. I mean, if I have a more than one slab, so this M1 dot M2 still holds for it?
I really don't understand what the question.
Sorry,
It has more than one slab, you mean?
No, I'm asking this another question, not related to this. If you have a planar slab, for that you are having a transfer matrix in 2 dimension, in which the components are in the operator form.
Yes, but this is not, this is one dimensional. But in 2 dimensions, you have a transfer matrix, which is an operator.
Yeah. So if we have 2 slabs in 2 dimension,
yes.
How does the composition properties of the 2 transfer matrix goes? Is it same as the way we do usually for the 1-dimensional potential? It just is it M2 dot M1 or it changes actually?
It is very, very similar, but you have to be careful. I mean, we have put a new paper which has just appeared in Physical Review A, which we give all the details of that transfer matrix, the composition property. Look at Physical Review A 2021. If you search my name, it's you can find it, or you can write to me. I'll send that copy if you wish.
Sure. Okay, thank you.
Welcome.
Joshua.
Hi, hello Ali. Thanks for your
Hello.
nice talk. Hi, a question about the wormhole. You have your solution in terms of those A of K. Can you actually calculate something which looks like quasi-normal modes of the wormhole? That should be singularities in the 3rd quadrant in K, I suppose. It should be zeros or poles of A, or in your solution, they should correspond to quasi-normal modes, which is an important thing in.
We only looked at the scattering problem. So
but you have the scattering amplitude as an analytic function in K. So can you find singularities in that function and therefore determine quasi-normal modes?
Hold on a second. So we were not able to solve the full scattering problem. So this is just for low energy
For low energy, yes,
solutions.
yes. For low energy, that's true.
And in that case, there's nothing blowing up.
Mm-hmm.
I mean, we have, here is the reflection and transmission amplitudes.
Yeah, that's true. Yes. Okay. Yeah, but maybe you can extend it somehow to analytical structure and try to identify those singularities.
Yes. The point is that, well, these results hold generally. That is, I have not fixed this function R of X.
Mm-hmm.
But if you want to do something like that, I mean, without knowledge of how this R of X behaves, I don't think you can do much.
No, but you can maybe prove some general theorems. So if R behaves like this, you will have poles like that.
Yes.
Things that sort.
But for each choice of R of X, this potential is one of the potentials that you can deal with ordinary quantum mechanics.
Mm-hmm. Okay.
One-dimensional quantum mechanics.
Yeah, that's why I'm asking if you can make more progress into those questions, which are not completely solved for. I don't think you can even do it for Schwarzschild black hole to find complete solution for these things.
No, I don't think so.
Mm-hmm. Okay. Well, thank you.
Frida has a question in the chat. You want to read it out, Frida?
Yeah, I had a lot of loud voices behind me. This is why I wrote it down. What is the physics behind the freedom of choosing the arbitrary length scale in a scattering problem? It seems that you are free to choose it. What is this freedom?
Oh, this is just, I just wanted to work with dimensionless quantities. That is the only reason. So for each specific physics problem, you can choose the relevant length scale. Like at the end, I chose the length, the thickness of the slab to be the relevant length scale. But at the beginning, when I discussed the general potentials, I didn't want to, I mean, I can't say which length scale is the relevant one. So I introduced an arbitrary L. But this is, I mean, change L, the end result, the physical results don't change. It's like a mathematical parameter I have introduced. In other words, let me put it this way. When we say low energy, what do you mean by low energy? Mathematicians just expand in powers of k. And for them, k is equal to 0 is low. But for us, k is not 0. So I have to compare it with something. Since in general, I don't know which scale is the one which I'm going to choose, I have just put it as L.
But I'm puzzled because if you have scattering lengths or something, it pops out of the problem. But here you just write it in the expression as if it is not there. So that is something which makes me wonder.
Well, I could, for example, just put L is equal to 1 here, and then you don't see it and nothing goes wrong. But the quantities acquire dimensions. See, that is what I did not like.
Okay. Any more questions, comments?
Yeah, Hugh Jones. I have just one comment on the one-dimensional scattering. Could bring. I think at one point you said you were talking about transparency or something, and you said T equals order k cubed. It's further along a bit.
Where was
I'm going. Actually, so it should be T equals 1 plus order k.
Yes.
That's all.
Yeah, I missed the 1.
Yeah. Okay, that's all.
Ali, it's Uwe asking a little question, just for curiosity. I'm not so deep in this business. when you compare your scattering problem with a usual Sturm-Liouville problem, for instance, over the real axis, as you also have it in the potential sensor, did you try to relate your problem to this Titchmarsh-Weil coefficients and this technology of limit point, limit circle technology? There should be some relation, I guess. I'm not sure. It's just for curiosity.
I have no idea.
Okay. Thank
I
you.
have no idea.
More questions, comments? Then let's just thank Ali again. Thank you very much, Ali, for the nice talk.
You're welcome.
Thank you very much.